We'll hear about A Tale of Two Crossings. I enjoy the title name. And that'll be given by Morgan McArthur of GeoEngineers. Go ahead, Morgan.
I want to start off by thanking everybody for sticking around until the end of the day here. I know it's been a long day, but you know, we've had some really fantastic talks with a whole lot of great technical information. It's pretty tough to follow up on all of that. So instead, I'm going to tell you a little bit of a story and sprinkle a little bit of technical information in here and there. I'm going to be talking about the Potlatch transmission line project that I worked on for Tacoma Public Utilities. Really, our work has been split into two different projects over the course of about 10 years or so, but I'm going to talk about them simultaneously. So it'll seem like they happened simultaneously, but they didn't actually. So I'll start off by talking a little bit about the project background and history, get into some of the original construction and some recent issues that came up that led to this project, talk about the design process with a focus on geotechnical information. Then I'll get into construction, do some real brief acknowledgments, and then hopefully there will be time for questions at the end. So the project is located in western Washington at the south end of Puget Sound in this red box area here. This is the alignment shown on the right. The project was constructed in 1925 to take power from the Cushman Hydro Project, which is at the south end of the Olympic Peninsula near Hoodsport, all the way across the Kitsap Peninsula and across Tacoma Narrows into Tacoma area. The alignment's approximately 40 miles long. It's got 4 major water crossings, the Suquamish Delta, North Bay, Henderson Bay, and Tacoma Narrows. It's a 115 kilovolt transmission line, which is comprised by 2 3-conductor circuits, which are supported on separate structures, but they're identical in nature. The upland portion is all supported on wood H structures, and then the overwater crossings are on steel lattice towers. So I'm going to be talking specifically about the crossings at North Bay and at Henderson Bay. These are aerial photos of the 2 project locations. As you can see, both of these are at the end of embayments or lagoons in the southern portion of Puget Sound. They're in very shallow water areas. The elevation at the existing tower locations range from about elevation -4 to -2 MLLW. So these areas are exposed or nearly exposed at low tides, inundated at high tides. Henderson Bay also the crossing at Henderson Bay spans across the Purdy Spit, which carries Washington State Route 302 over onto the Key Peninsula. And there is a low clearance bridge a historic bridge connecting the Purdy Spit to the town of Purdy there also. So next I'm going to do a little bit of a slideshow of some of the historic documents and photos, mostly because I find it really fascinating. This is a drawing of the original foundations. All of the in-water structures were supported on 4-legged concrete pedestals, which each supported a single lattice tower. So there were 4 of these at each one of the 2 crossings. Each leg of the pedestal was supported on a group of 3 timber piles. This is a couple of photos from installation of the original timber pile foundations. As you can see, they grounded the barges at low tide, and they did the majority of the driving during high tide periods. The piles were typically driven to practical refusal using a 2-ton hammer with a fall height ranging from 6 to 15 feet. The excess pile was cut off, and then the piles were bound together and the tops were cast into concrete. We actually have pretty good records of the driving, and it was really variable from site to site. And they even had some locations where they were using jetting to advance the piles through hard layers. So this is a couple of photos of the original or completed product. On the left, we've got Henderson Bay, and on the right, we've got North Bay. So these lattice towers were constructed in 1925. They've seen about 100 years of weather and salt and have some pretty significant corrosion issues. On top of that, you know, I had mentioned that the piles were typically driven to practical refusal. It turns out a few of them actually weren't. So at North Bay, it's hard to tell from this photo, but actually these two towers are actually tilting toward each other. They had tilted over time and were 2 to 3 feet closer to each other at the top than they were at the bottom. So that's kind of the impetus behind the project. So get into the project intent here is replacing the towers and the conductors at North Bay and Henderson Bay crossings with new in-water structures at each crossing. The team looked at multiple crossing options, including single, double, and triple span options. The idea was that the fewer in-water structures they could do, the better, but at the same time, they need to make it cost-effective with structure height and that type of thing. Also considering the construction access and how can we best put this thing together. Tacoma Power didn't want to have to go out there in another 20 or 40 or 50 years and replace this thing again, so they wanted a 100-year design life out of it. Also, because we're working with transmission lines and we're working in a marine environment, we're working with multiple design criteria. This is a list of the different design criteria that we were looking at. I'm not going to go through these in detail, but I do want to note that as a geotechnical engineer working in the Pacific Northwest, I'm used to the seismic design being often the most controlling case. For transmission lines, that's typically not the case. It's usually the combined ice and wind loading because it puts some really high moments on the poles. On top of that, these are both water crossings, waterfront homes. We've got some really nosy neighbors who have a really keen interest in what's happening and want to be involved in every single step of the way. So now I'm going to dig into some of the geotechnical related stuff. It really started with a whole lot of planning. You know, we're doing overwater explorations from a barge. A little bit complicated, but we do that often enough that we can handle it. But on top of that, we're in an area where we know there's a big tidal swing and we know that we're going to be exposed or nearly exposed at low tide. Our permits won't allow us to ground the barge. So we have to identify a time when we can get in and out on a single tidal swing in order to advance those explorations. We've got access issues. We've got that low clearance bridge at Henderson Bay, so we had to make sure that we could get low clearance equipment underneath it. We're working between active transmission lines, so we've got to be constantly cognizant of where our equipment is up in the air, you know, do short rod breaks when we're drilling, that kind of thing, so that we're not sticking anything up above the mast. On top of that, we're working in culturally sensitive areas, so we're working with an archaeologist who's constantly monitoring the explorations. Because we did a pretty thorough job of planning, we were able to advance all of these explorations without too many major hiccups. We did run into some artesian pressures that caused a little bit of heave, but we were able to handle that pretty easily. This is a cross-section of the subsurface conditions at North Bay. There's a pretty heavy vertical exaggeration. It's not actually that steep on the sides of the slope. But it's a pretty typical sequence for what we see in the embayments in Western Washington. We've got a series of loose and soft, interbedded loose and soft marine sediments overlying glacial sediments. There's a thin layer of glacial lacustrine silt before we get into very dense glacial till, and then we saw advanced outwash below that. In the advanced outwash, we did run into that artesian pressure I mentioned, but we actually didn't see any water flowing out of the drill stem. It was just enough to cause heave. At Henderson Bay, we had a pretty similar soil profile, except that the beach deposits here were thinner and more coarse-grained, which led to higher blow counts. Again, similar to North Bay, we ran into very dense glacial till, underlain by advanced outwash, and again, we saw artesian pressures in the advanced outwash. So a quick summary of the geotechnical conditions. We've got these soft and loose marine or beach deposits. potentially liquefiable under the seismic events that we're looking at. The thickness of those potentially liquefiable soils varied from site to site, as I mentioned. At North Bay, we had about 30 feet of potentially liquefiable soils. At Henderson Bay, it was more like 5 or 10 feet. Below that, we've got very dense glacial till, which can be a challenge for advancing driven pile foundations. And then we've got artesian pressures below the till, which can be a challenge for advancing or installing the drilled shaft foundations. So as we're doing the geotechnical analysis and stuff, the rest of the team is digging into the preferred crossing options. Ultimately looking, like I mentioned, at single spans with very tall towers on each side, double spans with a single tower in the middle, and 3 spans basically replacing the existing locations as is or nearly where they were, and arrived on the option of 2-span crossing with a single tall monopole in the center of each crossing. Each of these poles were between 160 and 180 feet tall, so they've got some pretty serious moments on there. But this enabled them to put both circuits onto one single pole in the center of the bay, eliminating 4 existing structures and replacing with one single in-water foundation, which played well from a permit and public opinions perspective. So for the in-water tower foundations, we looked at drilled shafts and driven piles, both small diameter, large diameter, bearing in mind the geotechnical considerations that ultimately were similar at both sites, but just different enough that we wanted to make sure that we're looking at different options for both sites. And we actually ended up arriving at different solutions for the 2 sites because of the different geotechnical considerations. At North Bay, we ended up with a 4-legged table supported on 30-inch diameter open-end steel pipe piles, 5/8-inch wall. They're coated for corrosion protection. The interior of each pile was also partially filled with concrete in case there was enough steel section loss over the 100-year design life. It was basically the redundancy, essentially. This tabletop design allowed us to take the high moments on that pole axially rather than laterally, because we didn't have a whole lot of lateral resistance out of the upper 30 feet of loose sediment. At Henderson Bay, on the other hand, we ended up going with a single monopile, 66-inch diameter, 1.25-inch wall thickness, also coated for corrosion protection, but here, instead of filling it with concrete, we went with a extra sacrificial steel section. So here, instead of taking the moments from the pole axially, we're using the stiffer soil profile to resist those laterally. So a little bit about the construction considerations, and some of them are the same as the geotechnical considerations here. We've got the tidal range. I mentioned there's some heavy tidal swings. We're exposed at low tide. The permit doesn't allow for grounding. We've got the low clearance bridge at Henderson Bay. You can really only navigate that channel at medium to high tide because there's not enough water to get large equipment under there. So it made it a challenge to get any sort of barges or that type of stuff through. And then we're working between active transmission lines, which obviously there's clearance considerations. But the design team and the contractors and Tacoma Power worked together to come up with a plan to install temporary piles and spread the lines apart to make a little bit larger work area there. Even still, you can see from the photo on the right, it gets a little bit hairy when you're picking up a long pile adjacent to an active transmission line. So both locations, we started pile installation using vibratory methods. At North Bay, the contractor used an IS-28C, which is a 2,800 inch-pound eccentric moment. On average, we were able to install those about 45 feet below mudline using vibratory methods, which is about 11 feet into glacial till. At Henderson Bay, we had a much larger pile. We needed a much larger hammer. So we used an APE 600, which is 17,200 inch-pound eccentric moment. We vibrated those to 33 feet below mudline, or about 8 feet into glacial till before hitting practical refusal. Then we moved on to impact installation. At North Bay, used a D50, an average of 8 feet of impact driving before running into practical refusal. Typical stroke there was 7.5 to 8 feet at end of drive with an average of 120 blows per foot. Each one of those were actually driven a few feet beyond planned tip. Still hit practical refusal, but they had a couple feet of extra pile, so just went ahead and drove past planned tip. At Henderson Bay, using a D100, we did 22 feet of impact driving, 93 blows per foot at end of drive when the contractor called that it was practical refusal. Didn't want to drive any further, and that was actually about 7 feet above design tip. So here we're relying on the lateral, so that gave us a little bit of concern. Were we going to be able to get what we needed? So we went through a process of confirmation at both sites also. At North Bay, we did both end of drive and restrike, PDA and cap lap. A little bit hard to tell from the scale on the chart there, but at North Bay, ultimate resistance as measured by cap lap was 1,190 to 1,350 kips. We needed 450 down, so we felt like we were in a good spot for each of those piles. From a downward capacity perspective, but we needed 250 uplift. And as you can see from the shaft resistance, we're a little bit close on restrike on a couple of those piles. We went through a series of analyses with the structural and ultimately decided that we had the factor of safety that we needed. It wasn't as much as we wanted, but we had a little bit of room to play still there. At Henderson Bay, because we weren't relying on the axial, we did not do a restrike cap lap, but we did do end of drive PDA and cap lap. And at end of drive, you can see we've got a ultimate downward resistance of 3,140 kips. Really, we only needed 310 kips downward, so we had a factor of safety about 10 on that. Lateral controlled, as I mentioned, so we needed to confirm that the embedment was going to be sufficient to get us what we needed for the extreme loading cases. So we looked at both seismic and the combined wind and ice loads, and ran through a series of L-pile analyses to confirm that we had the embedment. Ultimately arrived that we did have a little bit lower factor of safety than we would have loved to have had, but we were not going to ask the contractor to go out there and try to continue to drive this pile. So here's a couple of photos of the completed product. At North Bay, you can see they had not yet removed the original foundations when this photo was taken, but this is the final crossing. At Henderson Bay, it's pretty much a complete product there. A few acknowledgments. I'm not going to be able to talk about all of these people, but we had a really great project team, and I really enjoyed working with all of these folks. And questions, if there's time.
Well, thank you very much, Morgan. We have about 10 minutes before the beginning of the welcoming reception, so I think at this time we could probably accept a couple of questions since there's at least 10 minutes between you and the beer. Any questions for Morgan? And if you do, please do approach the microphone so we can hear the question. Okay, it looks like everyone's thirsty. I don't blame you. With that, I just want to say thank you for sticking around to the end of the session here. As you probably have noticed, we had some wonderful talks, some with local flair. I think that's a nice part about the SuperPile moving around every year. You get to see get both breadth and depth in the quality of the topics to see what we're all doing throughout the country. We have a full program tomorrow. It seems like we're going to be starting that with 2 parallel tracks at 8:30, so bright and early, and we look forward to seeing you then. Thank you very much. Enjoy the reception.